In the next few segments, we will be taking a deeper look at some of the commonly used latches and flip-flops. We start with the most basic of them all, the SR latch. SR stands for set reset. It is a latch which can be made using either two NOR gates or two NAND gates. We'll first look at how to construct it using NOR gates, then we'll see the NAND gate implementation as well. So the SR latch has two inputs, S and R, that is set and reset respectively, and Q and Q bar represents state. So Q represents the current state of this sequential circuit and Q bar is its complement. Again, remember that Q is going to be a binary value, it can either be 0 or 1. So it makes sense to have the complement Q bar. Now this is how an SR latch is set up. Two inputs and two outputs which are actually state, not exactly output, and this Q gets joined with the NOR gate for the S and the Q bar to the NOR gate corresponding to R. So this is called the function table corresponding to this latch. So function tables are defined for every latch or flip-flop. They tell you the inputs and the state changes that happen. So if these are the inputs I give, this is this next state my system will proceed to. So it's important to understand these tables exactly, in the sense that of course the contents of the table you need to understand how the latch works, but also this is function table, and after this you will be coming across two terms called characteristic table and excitation table as well, all of which are defined for sequential circuits only, and most of which have pretty similar columns and pretty similar values. So it's easy to get confused there. So function table, it tells you the inputs, and for this input what will my state be, next state be, that's all. Inputs, next state, and the complement of the next state, of course, that is no big deal. So yeah, we will now try to understand how this latch works with the help of these values. So initially when you have just powered on or switched on the circuit, there is no current state, right? It is just going to begin computation. So at this point we will just define the state as Q bar. We are not going to give it any value. We will start by giving S and R the values 1 and 0 respectively. S equals 1, R equals 0, and Q is connected here, Q bar is connected here. We do not know what the values of Q and Q bar are. For time being they are undefined. Now S is a 1, so my NOR gate will definitely give me a 0 irrespective of what my Q is. So Q bar becomes a 0, and now Q bar is a 0 which goes here. R is also a 0. 0 NOR 0 would give me a 1 here. So when I give S equals 1, R equals 0, irrespective of what my previous state was, the next state would be Q1 Q bar 0 in the NOR implementation of an SR latch. So I would like to repeat that. When S equals 1, R equals 0, in the NOR gate version of an SR latch, irrespective of what the previous state was, the next state becomes Q1 Q bar 0. Moving on, now this is our present state, Q1 Q bar 0. Now we will try this inputs, both S and R as 0. So S0, R0, Q is a 1. So 1 or 0 would be a 1 because it's a NOR gate, Q bar would become a 0. Similarly, this is a 0, Q bar was already a 0, 0 NOR 0 would be a 1. So 1, 0 again. So when we give 0, 0, we see that the previous state has been retained in this case. Now let's try giving 0, 1. Again remember that our present state is Q1 Q bar 0. Q is a 1, Q bar is a 0, R is a 1 and S is a 0. Now R is a 1. So my Q is anyhow going to be a 0 because this is a NOR gate. So an OR gate would result in a 1 if R is 1 irrespective of Q bar. Because this is a NOR gate, it will complement that 1. So my Q is going to be a 0. Now Q is a 0, it comes here. S is also a 0. Yeah, this third case we're doing, S is also 0. 0 NOR 0 should be a 1. So now Q becomes 0, Q bar becomes 1. And we did that using this previous state. But you will notice even for the opposite, if q had been a 0 and q bar had been a 1, you would still see that if s is 0 and r is 1, you would still get this. So again, another statement I would like to make, when S0, R1 in the NOR gate implementation of an SR latch, irrespective of what my previous or current state is, Q becomes 0, Q bar becomes 1. Again, now with this as the current state or present state, if we give 0, 0, we will notice that the same state is retained, 0, 1. Finally, again with this as the present state, we try giving 1, 1. Now, or with whatever present state you have, if you try giving S1, R1, both Q and Q bar would become 0, because this is a 1, so this becomes a 0, this is a 1, so this becomes a 0, and a number and its complement cannot both be 0, right? So we say the 1, 1 is an illegal state or a forbidden state, meaning you are not allowed to give 1, 1 as inputs. So to summarize the SR latch NOR implementation, whenever you give 0, 0 as the inputs for S and R respectively, whatever your current state is, it will be retained. You're not allowed to give 1, 1 as the inputs, it is an invalid state. Whenever you give S1, R0, you will get Q1, Q bar 0. And when you give S0, R1, you will get Q0, Q bar 1. The last two cases, irrespective of what your previous state was. So that is SR latch NOR implementation in a nutshell. Moving to the NAND implementation, the setup is very similar. You just replace the NOR gates with an NAND gate. And you will, I'm not going to explain the function table here because how it works is very similar to the SR latch. I would encourage you to take one pair of values at a time and trace out the working. Again, I'll give you the nutshell of it. Is the thing just becomes the opposite or the ulta of the SR latch. So here 0, 0 is your illegal state, 1, 1 will retain the previous state as such. When you give S1, R0, you will get Q0, Q bar 1. When you give S0, R1, you will get Q1, Q bar 0. That is the exact opposite of the NOR implementation. And these two again 1, 0 and 0, 1 inputs, irrespective of what your previous state was, this is the output you will get. So that is the NAND implementation. So if you felt this latter part of the explanation was a little too quick, I would encourage you to pause and try to take each pair of values from the function table and trace out the states just like we did for NOR gate. Now we are going to look at one more variation of the SR latch NAND implementation with control input or enable input. So what happens here is this part, if you notice, is similar to your NAND gate implementation. Over here you have your SR and you have something called the enable, which are connected to NAND gates and then connected to the original SR latch. So what happens here is, if your enable is a 0, then AND gate would anyhow give me a 0. So the NAND gate would give me a 1, right? So if my enable is a 0, both the inputs going to my, this is the original latch part, this is like a switch part. So if my enable is 0, both the inputs going to my latch would be 1, 1. And when it is a 1, 1 in an SR latch NAND implementation, we know it just retains its current state. No computation happens, no change of state happens when the inputs are a 1, 1. So when the enable is 0, irrespective of what my S and R values are, there will be no change. So this is like switch off position. Switch off in the sense you still retain, you don't forget the current state, you hold it in your memory but you do not perform any computation. When the enable becomes a 1, the values going are S dash and R dash, right? Those are the inputs. So this works similar to the NOR gate implementation. Why does it work similar to the NOR gate while we have used NAND gates here? Because if you get S and R values, this would be the function table. But here, through the NAND gates at this point, we are passing S dash and R dash. So the inputs are getting flipped, so to speak. So the function table for this enable input, it would have this one extra line. When enable is 0, no change, irrespective of S and R. and the rest, while the enable is 1, the function table would be similar to the NOR gate implementation of SR latch. So that is SR latch 3 variations in a nutshell.